Welcome to lesson 9.3 on conservation of momentum. This is kind of the part A. Now, a couple of things. When we're talking about the conservation of momentum, the basic idea here is that the total momentum of a system remains constant. Therefore, the system's momentum both before and after collision stays the same. So if we've got two things and they're colliding, the momentum that we have before is going to equal to the momentum after, regardless of what these things are doing. So the momentum before is equal to the momentum after the collision. A lot of times we'll use this little prime, which just means after, in indicating things before and after, because otherwise you just got a P equals P and it's not making much sense. But this says momentum before is equal to the momentum after. Now there are two types of collisions that we can have with that, the elastic and the inelastic collision. Now in both of these, the momentum does stay the same. So we're not taking a look at the momentum in this, but in fact it is the kinetic energy. The kinetic energy in an elastic collision is equal, meaning the total in the system before and in the system afterwards, where in an inelastic collision, they're not equal. The kinetic energies change. In other words, some of that energy that's in the kinetic store before the collision is going to other energy stores. Now that could be an elastic store, a thermal store, but that kinetic energy is going to other energy stores. Okay, so we're just going to watch this quick little video on elastic and inelastic collisions in order to kind of get an idea of the difference between the two.
I have two rubber balls that I'm going to roll down the ramp behind me and let the balls collide with the wooden block at the end of the ramp. The balls have very nearly the same mass, but very different elasticity. So when I drop the two balls, you'll see they bounce differently. Okay? Okay, so this ball is very bouncy, high elasticity. This ball, not very bouncy, low elasticity. So let's roll the balls down the ramp and see what happens when they collide with the wooden block at the end of the ramp. So first, the not bouncy ball, we'll roll it now. Collides with the wooden block and makes it shake around, but the block stays where it was after colliding. Now the bouncy ball, we'll roll it down the ramp and see what happens when it collides with the wooden block. Here it comes. So what is it about those two collisions that causes a different thing to happen to the wooden block? That's the question that this demonstration is meant to raise, and answering that question will help you understand conservation of momentum in a collision.
Okay, so what was the difference? The difference is essentially with the non-elastic ball, some of the kinetic energy is lost, meaning there's not a lot of kinetic energy going towards the block. And so with the non-bouncy ball, a lot of the kinetic energy wound up going to other energy stores. Where with the bouncy ball, it wound up knocking it over because the kinetic energy within here was mostly conserved. Now, the example there was not a complete, true, total elastic collision, but it was fairly close. And so this was the bouncy ball that knocked over the block. It was an elastic collision. The non-bouncy ball was an inelastic collision. Much of the kinetic energy went to other stores. So taking a look at putting this into some mathematical practice. And I find with these questions here, it's very helpful for you to just kind of draw it out first so that you kind of have an idea of everything that's going on. So we've got a 1 kilogram ball moving 2 meters per second to the right. So we're going to draw that 1 kilogram moving 2.0 meters per second to the right, and it's colliding with the stationary ball of 2 kilograms. So 2 kilograms. After the collision, so afterwards, the 2 kilogram ball is moving 1.2 meters per second to the right. And so what we want to know is what's happening with this 1 kilogram ball. Okay, so the momentum here has to equal the momentum here. Momentum before is equal to momentum after. So mv plus mv is equal to mv plus mv. Now, a lot of times you will see little 1s and 2s brought in here just for us to indicate everything that's going on. But if you can keep it straight, it's not necessary. Subscripts are not necessary. But you've got 1 multiplied by 2, and adding to that 2 multiplied by 0 is equal to 1 times v1 prime plus 2 times 1.2. So all of this together, you wind up with 2 kilogram meters per second, and it's got to be equal to 1 v1 prime plus 2.4 kilogram meters per second. So we're going to subtract the 2.4 from both sides, and that will get you negative 0.4 kilogram meters per second is equal to 1 v1 prime. And dividing by the 1 kilogram on both sides gets you negative 0.4 meters per second. That should be a 4. It's looking more like a 9. So we'll make that more like a 4, is equal to v1 after the collision. Now don't get distressed about this negative. Remember, that just means it's going in the negative direction. So this will wind up being 0.4 meters per second going to the left. Taking a look at example number 2, in this case, what we've got is these things wind up pairing together. So we've got this 6,000 kilogram moving 2.5 meters per second to the left, couples with an empty car that was rolling 3 meters per second to the right of 3,000. So we've got 3,000 moving at 3.0 meters per second. After the collision, all of these together, they wind up coupling, and so you've got basically one mass. And so in this case here, you've got mv plus mv is equal to mv, where this will be 1, 1, 2, 2, and this one is 1 plus 2, 1 plus 2. They wind up combining. So we're going to take the 3,000 and let's multiply that by positive 3 is equal to 6,000 multiplying by negative 2.5 is going to be equal to, well, that's going to be 9,000 v1 plus 2, the velocity of them combined. So this here is going to be positive 9,000 kilogram meters per second plus, and this here 6,000 plus negative 2.5 is negative 15,000 kilogram meters per second, which will be equal to 9,000 kilograms v1 plus 2. Combining all of this, you wind up with negative 6,000 kilogram meters per second, which will be equal to that, again, 9,000 kilograms v1 plus 2. Again, we shouldn't be worried about the negative. All that's indicating is left. And really, when we take a look at what's happening here, the 3,000 kilogram rail car had a momentum of 9,000 kilogram meters per second, but the 6,000 one had a momentum of 15,000 kilogram meters per second to the left, which means because this car, the 6,000 car, had more momentum, it's so kind of taking control of the system, and so all of this is going to wind up going to the left afterwards. Dividing by 9,000 kilograms to both sides, leaves you with a negative 0.667 meters per second, again being the velocity of 1 plus 2. So this is moving 0.6, well, I'll put just 67 meters per second to the left, or negative. The third way that these things can happen is you can wind up with a recoil or an explosion type of situation where you start off with two things together and they wind up separating. In this case, it's a gun and a bullet. So you've got a 5 kilogram gun and a 0.055 kilogram bullet. It's a 55 gram bullet. Afterwards, this gun is going to be shooting this way, and the bullet is shooting off at 300 meters per second. We're calling it west, so this will be east. Now this is the M1 plus 2, V1 plus 2 is equal to M1 V1 plus M2 V2. It's combined before the collision, it's separate after the collision. Now in this case here, we don't even need to worry about the combined mass because this was staying at 0, velocity of 0, so all of this is just 0, is equal to 5 times V plus 0.055 times 300 meters per second west. If you want to put a negative there to indicate the west and have east being positive, that's fine too. So 0.055 times 300 gets you 16.5. So you've got 0 is equal to 5V plus negative 16.5, or 16.5 is equal to 5V. Dividing both sides by 5, you wind up with 3.3 meters per second as being equal to the velocity. Now that positive is indicating that's going east, so you could say 3.3 meters per second. Okay, give this one a try, pause the video, see how you do, and we'll take it from there. Now, in this case here with the try 1, we had the smaller ball moving faster and the bigger ball moving slower. So we needed to really calculate to figure out what was happening with the velocity when they collided. In this case here, we do in fact have more momentum with this 1.1 times 10 to the 3 kilogram ball than we do with the 1,300 kilogram ball. Because it's moving faster, it has more momentum. We take the momentum of the one plus the momentum of the other equals the momentum of the combined after the collision. Now in this case here, we just calculate it out, find that this before the collision we had 840 kilogram meters per second of momentum is equal to 2,400 V. Divide by 2,400, you find that you have 0.35 meters per second east as your answer. Hope it helps, and if you have any questions, let me know.